So in the last video we come to this point. I will explain this diagram again. Suppose we have two energy levels. One is E naught I and one is E naught F. This is the highest energy level and this is the lower energy level. Here we have the magnetic field as 0. Now when an electrons make a transition, a jump from higher energy level to lower energy level, it emits radiation in the form of electromagnetic radiations, and its energy is equal to h nu, and this energy is equal to the difference in energy of the two energy states, E naught I minus E naught F. So h nu naught is equal to E naught I minus E naught F. From this we get the value of the frequency nu naught when there is no external magnetic field. Now this is the frequency of the line emitted when there is no external magnetic field. Now in the presence of magnetic field, once we apply magnetic field, then the total energy of the system, of the atom, will be now its initial energy, this energy which is E naught, times the potential energy stored when magnetic field is applied. So the total energy is now the sum of original energy plus the potential energy stored, where E naught is the energy of the atom when B is 0 and Vm is the energy, potential energy stored when magnetic field is applied. So from here E is equal to E naught plus Vm value is given by this equation 5, which is mu B, yes it's mu B not mu L, mu B BML. I can write it more clearly. E is equal to E naught plus mu B B into ML. Sorry. Now this is the energy, total energy of the electron. So once electric field is applied, magnetic field, sorry, then the energy of the atoms changed now. Now the highest energy level has energy E I, and the lowest inner states has energy E F. Where EI is equal to E naught I plus Bohr magneton is a constant. We have magnetic field, and then we have MLI. This magnetic orbital Compton number for highest energy level, and EF will be equal to E naught F plus mu B B MLF. EI is the energy of the higher energy level of atom when B is applied, and EF is the energy of the lowest energy level of the atom when magnetic field is applied. Now once an electron make a jump or transition from this higher energy level to lowest energy level here, then it emits radiation with energy h nu, which is equal to the difference in energy of the two energy states, EI higher energy minus lowest energy EF. So we can write h nu is equal to EI minus EF. In other words, if I use the value of EI and EF from these two equations, we have h nu, which is equal to E naught I plus mu B B MLI minus this term, which is E naught F minus mu B B into MLF. I can rearrange these terms. We have E naught I minus E naught F plus we have this term, these two terms mu b into b are common in both this relation, both these terms. This factor is common in both these terms, so I can keep it outside mu b into b. So here we have mli minus ml. I can write it as mu is equal to E naught I minus E naught F over H plus mu B B over H into MLI minus ML F. I can write it as, we have this value E naught I minus E naught F over H, which is given by this relation nu naught here. So we have nu is equal to nu naught plus mu bb over H delta ml, where delta ml is equal to mli minus ml f. Now we have selection rule for the change in this magnetic orbital quantum number. I can say that from selection rule only those transitions are allowed for which delta ml varies like plus minus 1 or 0. So I can say that delta ml value will be either plus 1 or 0 or minus 1. Now using these values in above equation now. Then we have nu naught is equal to, nu is equal to nu naught plus, if I put delta ml is equal to 1, we have mu b b over h. If I put 0, we have nu is equal to nu naught. And if I put nu is equal, delta ml is equal to minus 1, we have nu is equal to nu naught minus mu b b over h. Now this is for delta ml is equal to 1, this is for delta ml is equal to 0, and this is for delta ml is equal to minus 1. I will call this, let mu b b over h, mu b b over h, it's not b over h, sorry, yes, it's, the expression is eb, not mu b. I'm making some mistakes here. Mu b b over h. So yes, it's okay. Mu b over h is equal to, we have mu b value is, mu b is eh over 4 pi This is the Bohr magneton. So if I put this value here, we have mu b over h is equal to EH over 4 pi m into b over h. H cancel with this, so this is equal to EB over 4 pi m. And I call this is change in frequency, delta nu. Then these three expressions now modified to nu is equal to nu naught plus delta nu plus d nu, yes. And nu is equal to nu naught and nu is equal to nu naught minus d nu. This is for delta ml is equal to 1. This is for delta ml is equal to 0, and this is for delta ml is equal to minus 1. So we have three values of frequency once we apply the external magnetic field. So these three values are here. Now these are the three component lines. So it means that initially we have just a single spectral line with frequency nu naught when b was 0, and once magnetic field is applied, then this single line, spectral line, split into three component lines. One with frequency nu naught, this one with frequency this one, which is nu naught plus d nu, and one with frequency this, which is nu naught minus d nu. This is called sigma line, this is called pi line, and this is called sigma line. Now we will use the band diagram to explain this phenomena. So this is the quantum mechanical expression, quantum mechanical explanation of normal Zeeman effect. A single spectral line is split into three component lines, one with frequency equal to the original spectral line, and the other two has a frequency different from the original spectral line. One frequency is greater than the original spectral line, and one frequency is smaller than the original spectral line. Now I will explain by using the band diagram. Now consider two energy level. We consider two energy level, one with L is equal to 1 and one with L is equal to 2. And when electron jump from higher energy level, from this level to the lower energy level, here it emits radiation, and the radiation has energy h nu naught. This is the case when B is equal to 0. Now when magnetic field is applied, I will use a different page nowadays. When magnetic field is applied, then what will happen? Then we have ML values, because the orbital angular momentum now persists around this magnetic field. It persists around this magnetic field, and the projection is now ML. And the ML values now varies from plus L to minus L. Now for L is equal to 2, ML values will be 2, 1, 0, minus 1, minus 2. So it is how many values? 5 values. So it means that once we apply the magnetic field, then this energy level is split into 5 energy levels now. And when for L is equal to 1, ML has how many values? 3 values, 1, 0, minus 1. So it means that after the application of magnetic field, once magnetic field is applied, this is when magnetic field is 0. This is L is equal to 2, this is L is equal to 1, when magnetic field is 0. So we have a transition, only a single spectral line. But once magnetic field is applied, then this line, L is equal to 1 line, split into 3 sub-energy level. One with ml is equal to 0, one with ml is equal to -1, one with ml is equal to +1. Similarly, this energy level also split into 5. One with ml is equal to 0, ml is equal to 1, ml is equal to 2. Here we have ml is equal to -1, and here we have ml is equal to -2. Now the selection rule for change in ml is delta ml is +-1 or 0. So if we apply this selection rule, then the transitions are given here. We have a transition from here to here, because here the value is 2, here the value is 1. So delta ml is 1. 2 minus 1 is 1. The other possible transition is from here to here. For this ml value is 1, for this it's 0. So delta ml is either it's 1. And the third transition, possible transition, is this one. For these 3 lines, delta ml is always 1. Next we will check the value 0. For 0, the possible transition is this one. It can be this one. It can be this one. For all this transition, delta ml is 0, because here the ml value is 1, here the ml value is also 1. So 1 minus 1 is 0. Here the ml value is 0, here the ml value is also 0. So the transition gives us delta ml is equal to 0. And here the ml value is -1, and here it's also -1. So delta ml is also 0. So here delta ml is 0. And the transition for which delta ml is equal to -1, it would be from 0 to 1, or from -1 to 0, or from -2 to -1. If we calculate delta ml for these 3 transitions, it will be -1. So this is the quantum mechanical explanation of normal Zeeman effect. Each spectral line is split into 3 components. So the quantum theory completely describes the normal Zeeman effect. I hope you understand this topic. Thank you.